There are two trends in nature. The first one has to do with energy. Energy goes from high energy to low energy. So this is an example of a lit match, and we blow it out and then it cools off. Energy is also known as enthalpy. And it's given this symbol H, and the H is found right in the middle of that word. The second trend that we're going to talk about now is disorder. So disorder has an S in it. Its other name is called entropy. Notice that entropy does not have an H in it. So entropy has to do with disorder, and you just have to memorize that. The symbol for entropy comes from the disorder, and that is a delta S. And it's the concept that everything in the universe is becoming less and less organized, or more and more disordered. So in a previous goal, we've already talked about enthalpy. You can find enthalpy using this equation, products minus reactants. And again, those are looked up on a chart. And if you calculate it and it is found to be negative, then you know it's exothermic. If it is positive, that means it's endothermic. And again, there's a tendency in nature to move towards a lower energy. A second way that you can calculate enthalpy is through using the Q equals mc delta T formula. And if the Q ends up being negative, then you know it's exothermic. And if the Q of the reaction is positive, then it would be endothermic. Let's dive deeper into this concept of entropy or disorder. Remember, disorder is a delta S. And let's look at a situation where we had one atom of gas, and it is in a container that has a left-hand side and a right-hand side. So where would that one atom be most likely to be? And you would find that 50% chance of being in the left-hand side or in the right-hand side. Now, what if there were two gas atoms? Where could they be? They could be stacked up on the right-hand side or stacked up on the left-hand side. But your most likely scenario is that they would be evenly distributed. So that randomness of just colliding with each other in the size of their container, they would end up having an equal possibility of being on the left-hand side or the right-hand side. Taken all together, you would see that there is more likely a chance of them being evenly dispersed. And let's apply this now to 4 atoms. So if you had 4 atoms, where are you going to find those 4 atoms? Yes, they could be stacked up all on the right-hand side or all on the left-hand side, but your most likely scenario is that they are going to be evenly distributed. And so there's all the possibilities there. So in entropy, when we're studying that, there's a tendency to go to the most disorder. And we have most disorder when things are evenly dispersed. Notice the equation to find your change in entropy. It's just like that change in enthalpy equation. So sum of the products minus sum of the reactants. The values, the positive, negative, you need to know. You need to memorize these. If we have a positive value, this is an increase in disorder. Remember, delta S means disorder, or it's also entropy. If we have a negative value, that's a decrease in disorder. So I know it's kind of a double negative. So you're really increasing the order, but to keep consistent, delta S is disorder. So we have a decrease or a negative disorder. In the universe, the disorder increases. So it is continually getting more and more disorganized. So this is very different than the law of conservation of energy, the first law of thermodynamics, where energy is conserved. It's just changed from one form to the other. In the second law of thermodynamics, we have that the entropy of the universe is increasing. We can calculate our delta S by taking the sum of the products and minusing the sum of the reactants. So let's go ahead and do this. So we have on our product side, and this one's our reactant side, our product side we have 2 moles of our NaOH. So that would be 2 times 50. And I'm going to add it to 1 mole of our gas right here. And I like to keep all my products in brackets to keep it separate. And then we subtract our reactants. So in our reactants, we have 2 moles of the sodium, and add that to 2 moles of the water, and we can do our math. And our answer is a negative 11. And our units are a little bit different than what we've seen before. It's joules divided by Kelvin times moles. So our entropy is very, very small. So it's in the joule unit. So watch out for that. Later on, we're going to have a formula where we combine the delta S and the delta H. And so you'll want to make sure that you're in the same unit. So what does this number tells us? This number tells us that we are decreasing disorder. Decrease disorder. Besides doing a formula to find the entropy, you also can just look at the state of matter. So when you're looking at a solid, those molecules are vibrating. So when you draw a solid, we draw it kind of in a regular array. But that's not really what's happening. Instead, they are vibrating in place. So they might be a little bit closer to each other or a little bit further from each other. A little closer here, a little bit further here. So in other words, they're vibrating in place. So there's a little bit of disorder there. Obviously, the colder it gets, then the less vibrations they will have. So if you look at the entropy of a pure crystal, it will be 0. But that would only be at absolute 0, 0 Kelvin. When you take and heat this solid, you're going to have even more randomness. Where are you going to find that one atom? Well, you could find it up here, or it could travel over here, or it could go up here. But there is some order there. The molecules are touching. There's some intermolecular forces between that are keeping it as a liquid. And so that stickiness is going to be there and keep it as a liquid. As we go to a gas, those intermolecular forces are going to not be there. And so there will be even more randomness. Where will you find that atom in the container? You'll find it all over. Okay? And so you have even more disorder with gases because there are no intermolecular forces. So solids, liquids, and gas, we have an increase in entropy as we travel through the different states of matter. Let's go through these examples, looking at the states of matter and also the number of particles. And we can determine just from looking at the bounce equation and those states of matter if the entropy is increasing or decreasing. Looking at the first example, I have a liquid going to a gas. So this would be like boiling water or water evaporating. And because I'm going from a liquid to a gas, I'm increasing my disorder. On this next one, I have one molecule, but here it's going to 2 molecules. So that's an increase in disorder. Also, I'm going from a liquid to gas particles. So 2 ways it's becoming more disorderly. Heating a metal bar, so as you heat atoms, there's more vibrations, so more different probabilities of whether those atoms will be closer together or further apart or going up and down. So this is an increase in disorder. And in this one, we also look at number of molecules. So we have one molecule here where it's together, and then we have 2 molecules that are separate. So because they're separate, then I have more disorder or more probabilities of finding them in different places. When they're stuck together, you're always going to find them together. So they might be moving around the container, but you're always going to find one next to the other. If I separate them, this will increase the disorder because there's more probability of where you might find them. So they might be a little bit closer together, a little bit further away. And the last one, going from a liquid to a solid, this is a decrease in disorder. It's becoming more orderly. So just looking at the states of matter, the number of particles, you can tell if the entropy is increasing or decreasing.